Okay.
So we'll just start with EEG. This is the one that people tend to be more familiar with, and it's non-invasive, it's inexpensive, and it's typically in more widespread use than ECoG, so it's a good place to start. We'll introduce just some of the basics of the signals and the equipment that we see in EEG, and touch briefly on some examples of EEG use in sleep medicine, in brain-computer interface, and in monitoring the depth of anesthesia for surgery. Time permitting, we'll go on to some of the cool stuff that's happening in electrocorticography. This is also known as intracranial EEG. This is, much to many people's surprise, also done in humans, not just in animals, and it typically is used prior to invasive brain surgery for mapping brain function before tumor resection or targeting intractable epilepsy that's medication resistant. We'll go through some of the signals and some examples from epilepsy brain mapping. Both of these are electrical recordings. That means they're referential recordings. It means you're taking a recording from one location, a signal source. This is showing an intracranial, but the principles are the same for scalp EEG as well. You have a signal against a reference location, which gives you a difference in charge that we measure as a voltage potential difference with potential equalization against a ground. The big thing to remember about this is that in referential recording systems, it matters where your signal is with respect to your reference. So the recording you'll get putting a signal electrode here versus here against the same reference will give you a different voltage. That's how the systems work. In EEG, we typically have standardized ways of applying these to measure signals across the scalp. Depending on neurology or sleep medicine, you might have different kind of tweaks of this, but they're all based off of what's called the International 10-20 system. It's just a system of measurements based off of percentage differences. So you might make a measurement from the nose, the mesium, to the back of the head, the inion, and then meter out electrodes in between at intervals of 10 and 20% of that distance. Each EEG electrode is measuring quite a lot of brain activity. So if we look at a projection here of the 10-20 electrodes in each black dot onto a representation of a human head there, each one of those is actually looking at the kind of spatially summed average of up to 6 to 10 square centimeters of cortical real estate. So quite a lot of neural activity goes into the signal that each one of these electrodes will record. Here you can see how much distance there is between an EEG sensor shown in red at the top and the cortex where we're getting brain signals at the bottom. And this tissue in between acts as what we'd call a low-pass filter. It means that only low-frequency activity manages to get through all of this tissue into the recording electrode. So it limits the amount of information that we can get from EEG signals. We've essentially kind of truncated the amount of information that an EEG sensor can see because it's so far from the source of the signal itself. This is in contrast to something like ECoG, where you place arrays of electrodes directly on the cortical surface or even inside the cortex itself, depth electrodes you would call them. And the signal fidelity, the quality of the signal you get when you're that close to the neurons you're measuring from is much higher. It gives you a much broader band of information that you can play with. So you can do some things with ECoG signals that you just fundamentally can't do with EEG. And this is kind of the trade-off between EEG, which is, as we said, non-invasive, inexpensive, widely used, and something like ECoG, which requires an extensive, invasive brain surgery to place the equipment in the first place. Another trade-off you can illustrate by considering what you would get with a single neuron recording. This would be maybe what they would call a Utah array, microelectrodes placed into the transverse plane of the cortex. So you're right up against the neurons you're measuring from a much smaller population. Your fidelity, again, is much, much higher than, say, ECoG or certainly EEG. But the trade-off is you're only looking at this very, very small patch of cortex. So if you have a continuum, EEG is looking at a lot of stuff at the same time, which can be helpful. ECoG is looking at a smaller area, and you can zoom in even further and look at single unit activity and look at a very, very small area. Better fidelity, less area of activity. That's technically typically the trade-off that we see. Some of you may or may not recognize Stephen Colbert. He's a late night host now. This is wearing an EEG cap from the brain-computer interface lab that I did my doctoral work in. He's not actually hooked up to anything right now. You can see that the cap is actually quite old. Some of the newer caps look more like this. And they get signals by filling the electrode cups here that you have placed directly against the scalp with some conductive gel. And that gives a good contact electrically between the signal source and the sensor that you have at the scalp. There are wireless EEG systems these days that are pretty good. You sacrifice some signal fidelity when you're compressing something to be transmitted wirelessly. And of course, that has to be hooked to a battery, so there's a limit on how long you can record. But these systems are great for research because they're so portable. That's a GRASS Model 6 polygraph, it was called. This is technology that's about 40 or 50 years old, and this is what you would need to get maybe 6 different EEG channels at the time, versus the system at the left here. It's wireless, it has sampling rates up to 500 hertz, and can record up to 64 channels. So the technology is just, I mean, the miniaturization to me even is amazing, and I'm a young guy. There are also some of these dry electrode systems that you might hear about, and I'm sorry if I saw some hands go up. I'll keep looking, it's okay. These systems are nice for ease of use. You can just kind of put them on. There's some work actually being done here in the Boston area looking at something called a STAT EEG. And in the emergency room, a neurologist might want to get a quick brain read, and systems like this that don't require that conductive gel to be put under each lead can be applied very, very quickly. So that's one area that people are looking into to make EEG expediently accessible in an emergency situation. There's a few different ways that we like to look at EEG signals, and I think they kind of map nicely onto some distinct clinical and research examples of what we use them for on a day-to-day. The first is just visual inspection. This is a picture of Hans Berger, who first described something called the alpha rhythm, which you see at the top and here on the right. And this is an EEG signal from 1924 and then reported widely in 1929. So almost a century ago, we were looking at these signals. And it was immediately apparent that they tracked behavior and brain state in interesting ways. So the difference between what's left of this arrow here and what's right is whether or not the subject had their eyes open or eyes closed. So already, without having to do any fancy math, you can tell that these signals are telling us meaningful information about what the brain's doing, in terms of, at least in this case, behavior. It also tells you something about brain state. So it didn't take long for people to realize that tracking these alpha rhythms in an awake brain, watching for when they disappeared, here at the second, or the fourth down rather, you could mark the transition between an awake subject and an asleep subject. And this spawns the beginning of a whole explosion in sleep research. It happened mostly in the 1950s and 1960s, trying to classify different stages of sleep using the EEG in conjunction with other electrical signals like the EEOG, which is an eye signal, electroocculogram, and the EMG at the bottom, that's the electromyogram for muscle activity. Combinations of these signals can be used to determine the depth of sleep of a subject. So here you see the alpha rhythms we're talking about before in an awake brain. Moving one down, you see waveforms that are characteristic of light sleep. That's called a K complex. The K comes from, they were discovered when noises would happen, and you'd see this K complex emerge, and the K actually is short for knock. Someone knocking at a door, and your brain produces this signal. And it's thought that that response is a way for the brain to keep you from being interrupted out of sleep when just kind of light and non-threatening things happen in the world around you. They're also defined by a sleep spindle. This one particular waveform is specifically what I study, and that's maybe a whole other story, but this is a lot going on with the brain during light stages of sleep and processing memory, preparing cognitive function for the next day, and processing things that have happened in the previous day to integrate with previous experience. And all of that's reflected in these sleep waveforms we see, K complexes, sleep spindles. If you're in a very, very deep stage of sleep, you see these distinct slow waves. In fact, this stage of sleep is often called slow wave sleep because of these very slow, large amplitude waveforms, about 1 to 4 cycles per second. Other stages of sleep are characterized by eye movements. So we can look at how quickly your eyes are moving, and this is most famously associated with what we call rapid eye movement sleep. It's a very light stage of sleep that's typically associated with dreaming. Changes in muscle tone also help the sleep physiologist identify the particulars of which state you're in. We can take all of that information together and start to form a picture of what somebody's night of sleep looks like. And so here on the y-axis, we're looking at essentially depth of sleep. You're awake at the top, and as you start to fall asleep, you drop into successively deeper stages until you hit, again, that slow wave sleep that we see there. You tend to lighten up towards the stage 2, where you have those K complexes and sleep spindles working on memory during the evening. And then REM sleep associated with dreaming. The EEG is actually interestingly indistinguishable from the waking EEG. So without those other signals we talked about, the eye movements and the muscle tone, it's absolutely indistinguishable if you're looking at a brain that's dreaming and a brain that's 100% awake, which was something when I was an undergrad I thought was really, really neat. Just quickly what these signals look like. This is a typical recording of someone hooked up with EEG before a nap, done here at the center. And we're looking at here, wake, eyes closed, because you can see this very characteristic oscillatory activity in the alpha band there. If we move a little further along, we can look at that stage 2. This is that light stage of sleep that has K complexes and sleep spindles, which, as we were saying, are important for processing memory during the night. And there, again, this is all from visual inspection. So an entire field of half a century of work is done looking at how these things change according to the human eye before, fast Fourier transforms and spectral decomposition was available. This is that slow wave sleep we were talking about. So moving from visual inspection to slightly more sophisticated methods, one popular research method actually is evoked response potentials, and this is a way of looking at brain signals in response to some reference event like a stimulus or behavior, and it operates on the principle of cross-trial averaging. Simply the idea that brain signals are very noisy, especially EEG signals with all of that scalp and skull in between, and by measuring the exact same thing several times and averaging the result, you can filter out the noise and reveal the underlying signal in the cross-trial average. This is a stimulus evoked response potential example. You might have this red light hit the optic nerve, travel through the LGN and the thalamus, and project the visual areas in the back of the brain here. And if we measure the EEG, you see deflections, negative, positive, negative again. We call the visual evoked potential. And if you average a dozen, 2 dozen trials together, this will start to emerge in the resulting average. That's kind of interesting. What's even more interesting about ERPs is that they can track higher cognitive function, things that are what we call cognitively irrelevant, things like attention. So if I told you just to pay attention to what you're seeing, your brain's going to produce a visual evoked potential no matter what it is. If I tell you to pay attention to a specific letter and a string of letters I flash on the screen, and you're looking for the letter A, I might flash a bunch of random letters and your brain gives you this visually evoked potential. Only when it sees the one you're looking for do you get what we call the P300. P stands for positive, this is very simple nomenclature here, and 300 for the time delay that the peak occurs at. So this is 300 milliseconds after the stimulus. And the key being that if it's the thing that you're expecting to come, you get a P300. If it's not, your brain doesn't produce that potential. And this has some really interesting uses, like some of the first brain-computer interfaces which were developed to enable people with neurodegenerative disorders like Lou Gehrig's disease, amyotrophic lateral sclerosis, or ALS, to be able to communicate after their motor systems had devolved to the point where they couldn't control the output of their limbs, for example. So this is an example of a brain-computer interface, or a BCI, working on exactly the principle we just discussed. This person is thinking of a letter, O, W, E, and every time the computer detects that P300 response, it enters that character into the text box above. So you have a person here typing fairly quickly just by their thoughts. And this is a concept that's been around for 25 years. This is nothing new. And it operates on EEG, which still tends to boggle my mind because the EEG signals, us people who are in ECoG research tend to be snobby a little bit about EEGs. They can be very dirty, low fidelity signals. But the fact that you could do this, I think it's still amazing to me. These days you're going to hear a lot about spectral analysis if you look at EEG signals. And this is based on something called the Fourier transform, which is just a mathematical trick where we can take an unprocessed signal, something like this in what we call the time domain, and decompose it into series of sinusoids or component waveforms that when you add them up give you the constituent signal you derived them from. So one way to visualize that would be taking this time series EEG signal and splitting it into different frequency bands. This is a slow component, so about 1/10 of a cycle per second to 1 time per second, or 1 hertz. This is that algorithm again, 8 to 12 hertz. We can take each of those extracted components and then line them up in what we call a power spectrum. And this tells us from frequency 0 to, in this case, 30 hertz, the relative power or amplitude of the signal constituent at that frequency. And I think this is a great way to visualize it. I found it on Wikipedia of all places, and it's a really nice conceptualization of that red time domain signal. Deconstruct it into constituent cosines and sinusoids, split them out. Now we can take a look at the amplitude of each one. This is the Fourier domain, or this is the frequency domain, and this is a power spectrum conceptually. So that's exactly the same as what we were just looking at right here. Again, and what this is telling me, I'm looking at this and seeing that there's a lot of low frequency activity in this brain signal. There's a bump around 4 hertz here, and then there's another bump around the alpha band here. That's fairly typical of most EEG channels, regardless of where you put them on the head. Now we can take that slice, and we can do that for each unit of time, and make this kind of three-dimensional representation that tells us the power at each frequency along each unit of time on this axis. So we can look at how brain signal spectral power changes over the course of an experiment, over the course of a night. Taking that same 3D plot, what's more common than that these days is to look at a two-dimensional representation. So we've gone from this one slice, put that here, stacked up a bunch over time, and then just stood it on its end right there. And what you're seeing in the white is basically the limits of about 95% of the signal in this case. And this is a nice example from a review from Emory Brown, who's a fantastic guy in Boston. He's doing his work with Harvard Medical on anesthesiology. And he's looking at how spectral decomposition gives him an advantage as an anesthesiologist, looking at maintenance and suppression of brain activity during and after procedures that require anesthesia. So here, in this case, you're seeing at the bottom the time domain representation of these EEG signals during an anesthesia operation. This is actually an experiment, excuse me. And here you can see how the spectrogram representing the relative contribution of these different low-frequency and high-frequency components changes as the brain goes from unanesthetized, fully conscious, to drowsy, to completely anesthetized. And this drowsy state is what we see here. It's called a maintenance activity. This is dominated by that 10 hertz alpha rhythm again. Over here is a burst suppression mode. Now, anesthesia isn't my area of expertise, but by the time you get to this area, you're having brain activity that's basically interspersed by these what we'd call isoelectric points of zero activity, essentially. So this is an example of somebody going from consciousness to complete anesthesia to a drowsy state where they're still able to intermittently respond to stimulus. And all of this is easier to track by eye when you're looking at the spectrogram than the actual signals themselves, and also allows computers to do quantitative analyses that are a little more empirically principled than we would get from visual inspection. I think I gave a lot to you very fast. Do we have any questions? Anything we want to go back for right now before we move on to ECoG? The answer can be no.
Can you re-explain how you took apart the sine and cosine things again? Like the 3D part?
Yeah, let's go back to that. This is something that took me a while to get my head around as well. Where is that animation? So I'd like to just start again with conceptually. We can figure that this signal is composed of a whole bunch of different frequency sinusoids laid over each other. So here you're seeing a low frequency component and then the faster frequency components. And you'll notice that each one has a different amplitude. And so there's a formula for translating essentially this signal into the relative sinusoids and then measuring the height of each sinusoid. And that's what we'd say is the spectral composition of that signal. So each one of these, again, is representing an oscillation with a different size and a different speed, fast or slow.
So
and if
you're
you
measuring the max amplitude of that sine wave, and that's
conceptually, yes.
okay.
Yeah. So just because you can see it, the amplitude of that low frequency one is much, much higher than the fast frequency ones, and that's why you get the largest line to the left. That's actually something that's pretty common in brain signals. We call it what's called a 1/f power spectrum, meaning that the higher the frequency, the lower the amplitude, which if you're a physicist, you would associate that with something called pink noise. I can send some follow-up if anyone's really interested in the details. And if you're interested in the math, I have some good review articles that I'd be happy to send.
Okay, sure.
Did that get any?
Yeah.
Okay. I'll just briefly pause on this again, since sleep research is near and dear to my heart. We saw this example, hypnogram we called it, of depth of sleep, lighter sleep, deep sleep, and the red dreaming sleep. This is an actual example rather than a cartoon of some data I'm working with. And one of the things about breaking these things out into the spectral domain, again, is it's a nice way to distill very complex signals into very simple patterns that pop right to the eye, right? So anyone can look at this and say, there's something going on here that stops right there, and that the brain is doing very different things here versus there, which again you can see mirrored in the hypnogram. This is when they're awake. This is when they're in light sleep and when their brain's working on memory processing. So you can get a sense over the course of an entire night, this is about 13 hours, about how the brain cycles between periods of wake and light sleep, where it processes memories in a particular way, deeper sleep and dreaming sleep, periods of wakefulness in between. And if you study it even closer, you'll be able to tell that the REM sleep, the dreaming sleep, and the awake looks utterly indistinguishable again, which is something that is fascinating to memory and sleep researchers, has been for quite some time. Yeah?
According to the data, which time period you may suggest people to sleep?
Meaning what time of day, or?
Just between the 11 p.m. to the 7 a.m. Because some of the people want to do their work very late, and maybe they don't have to sleep, or they wake up tomorrow and they don't have much energy. So, which time period you can suggest that?
It's a great question, and the answer is probably more complicated than either of us would like. There's no answer for everybody that's the same. There's a lot of individual variability in morningness or eveningness, we might call it. So first, I like to get up early, and my brain might want to go to sleep at 9:30 at night and get up at 5:30, and someone else's might want to go to sleep at 1 in the morning and get up at 11 a.m. And that's perfectly fine if that's what their body is naturally inclined to do. It's further complicated by the fact that that changes across the lifespan. So I don't know if any of you know any teenagers. They typically are pretty sleepy. At least in the States, they also have to go to high school at like 6:30 in the morning, which research shows is basically the middle of a teenager's night. Their brain wants to be asleep. So what we would say that from childhood to the teenage years, you become more and more of a night owl, more and more inclined to getting more benefit out of sleep when you're sleeping later and waking up later. And then during the adult years, you'll start to come back towards an early rise time and an early bedtime. The most important thing is to get more or less 8 hours. Another point I'd make on the sleep and memory stuff, all that studying you do during the day, if you don't get a good night's sleep for your brain to kind of chunk it, parse it, and remember it, a lot of that effort goes to waste. So the whole concept of cramming before exams, you're really not doing yourself any favors because you're trying to get a lot in at once and you don't give yourself the sleep you need to fully process it. Maybe that's kind of a life hack. So I wanted to talk about electrocorticography a little bit. It's in principle, it's the same as EEG, it's just that you get to put your sensors right on top of the brain, which lets you do some really interesting, cool stuff. So again, in comparison, we had scalp sensors for EEG that were located on the scalp with all of this tissue dampening and filtering the signals we record at the surface. With EEG, we're right on top of the cortex, and the signals do not get cleaner than that, which means you can do some pretty interesting things. Is that clock correct? Yeah. Okay. So compared to EEG, we have these sensors on the surface. They're looking at a very large patch of cortical real estate. And if we look in contrast to electrocorticography or intracranial EEG, this is actually data from a patient that I've projected onto a reconstruction of the brain. This is a generalized template brain, but the electrodes are actually representative of patients that I worked with in grad school. And each one of these gives you much, much higher resolution than the EEG signals we were looking at before. And more importantly, it gives you the higher fidelity, too. So the amount of information that we get in these signals is much, much richer than you could ever get at the surface. It's a signal processor's dream. Why do we use these things? They require pretty extensive invasive brain surgery to implant them. This is an example of a craniotomy where they remove a large patch of bone in the skull, which sits next to them at a table for several hours while the surgeon does a first procedure to put electrodes in, and then eventually the goal is to perform this resective procedure. So you might have somebody with a brain tumor. You might have somebody with medically intractable epilepsy that's become resistant to any of the kind of epileptic treatments that are available in pill form. And the goal, of course, is to identify either the tumor tissue or the source of the epileptic activity and remove it so that you can treat the disease. And just in this picture, you can see that these surgeons are removing quite a great deal of brain tissue in these procedures. It means the surgery is effective, but it also introduces some complications. Here's another example from a patient I'm working with right now. Commonly in these cases with intractable epilepsy, they'll go in for one procedure, they'll have some brain tissue removed. In this case, you could see the entire frontal pole of the left temporal cortex has been excised, and that successfully treated this patient's epilepsy for about a decade. But as is often the case with these patients, as time goes on, that epileptic tendency of cortical tissue will start to kindle somewhere else, and eventually will hit a point where it's resistant to medication again. And they'll often come in for 2, 3, 4 of these procedures over the course of their lifetime. And each time they do that, there's a trade-off, like most things in life. The most effective treatment of epilepsy ever devised is to remove the whole brain. There's no epilepsy after that. But your patient probably won't be too happy with you. So on the other extreme, if you remove nothing, the disease continues to progress and gets to a point where the quality of life from epilepsy are virtually intolerable, we hear from these patients. So somewhere in the middle, defining that trade-off boundary between what's the right amount to treat the disease and what's not too much to impair function is an active area of research and dates back to mapping procedures that were developed largely at the Montreal Neurological Institute in McGill, Montreal, Quebec, by Wilder Penfield in pioneering research with stimulating the brain to map cortical function. So, fortunately for epileptologists and surgeons, a lot of brain function, regardless of whose brain it is relatively stereotyped in terms of location. So the motor strip in you is pretty much the motor strip in me. Same with sensory regions. And in general, more or less, Broca's area, which is involved in language production, and Wernicke's area, which is involved in receptive language functions, understanding, essentially. Visual cortex is also fairly stereotyped. In fact, out of all the cortical hemispheres, it's probably the one that's best well understood at this point. Despite the stereotyping, there is actually, again, significant individual variance in the precise location of these. And one other thing you might notice is that all of these locations that are functions that presumably you would not want a surgeon to remove are adjacent to the temporal lobe where most epilepsies occur. So essentially, this is a part of the brain that a surgeon's going to want to explore for treating your disease, but at the same time, they're going to want to be very, very careful about preserving the parts of your brain that are responsible for these very, very important functions. Now again, the early work was done in the early 1950s, late 1940s. This is an example of a modern-day reconstruction. There's a patient's brain after a craniotomy, the electrode grid afterwards. This is what you would see in a CT. And then by using some software reconstructions, in fact, this cortical reconstruction was done using the FreeSurfer suite developed here at the Martinos Center to take a structural MRI and then co-register it with the CT so that we can get an idea of exactly where each of the ECoG electrodes is on that person's brain. Now, the gold standard in mapping with this technology is electrical cortical stimulation. And it's the same thing that it has been since it was first done in the 40s and 50s. And in fact, the devices that have FDA approval haven't changed largely at all in all of that time. And the procedure itself is fairly simple. It's what we call a lesional approach, which means the idea is for the epileptologist to work with the patient to generate a series of behaviors and then try to essentially interrupt those behaviors with electrical stimulation. And the idea is very simple. If I zap this part of your brain when you're doing it and you can't do it anymore, then that part of your brain must be necessary, not just sufficient, but necessary for that function. So that would be an area you would want to tell the surgeon to stay away from. This is an example.
At 3, it's just going to go first. Relax.
Oh, whoa.
Yeah. So somewhere, around 2, you saw a mild tremulousness.
Okay, I didn't like that.
No, we're not going to do that anymore. That was hand, ulnar. Stick out your tongue.
She's sticking out her tongue.
Yeah, what's that about?
Tongue protraction. And as soon as he stimulates,
I think it's me. Stick out your tongue.
she can't keep her tongue stuck out anymore. It's been back into her mouth.
Keep it there, keep it there. Okay, relax. Okay, and then I'm going to ask you to do it. Hold on a sec. Do it one more time. Keep it there, keep it there. Oh. Okay. Okay, so, alright, so you got... Can you, sing a note? Like the and sustain it. In other words, like when I ask you to, can you just say, okay. Try again. Hold on a second. All right, sustain again. Go ahead. That's pretty good. Try again. One more time. Try again. Okay, that's good. Okay. So I'm going to think more laryngeal. So in your
Okay, so you can already get a sense that this might take some time. And if you have 100 or so electrodes implanted and you have to do a pairwise stimulation for each one, it can take hours. These typically take on the order of 3 to 8 hours, sometimes 2 days. Places like Yale have Medical Center where they implant 200 electrodes, each of which they put in a lot of electricity in the brain, and it's very common in these mapping procedures to actually elicit a seizure. Particularly at a grand mal level, can be life-threatening. So he's calling for Ativan right now, which is a quick way to put down an epileptic brain. You might ask, there must be a better way. As I said, this procedure has not changed since the 40s and 50s. It's the same way it's always been done. It's done that way because it works, but it's labor intensive. It presents certain morbidity risk with the patient, and there's a likelihood of eliciting a seizure, and it's lesional, so it can only prove a negative in that way that, again, necessary versus sufficient. So turning back to our ECoG channels, I've said a lot about how rich the information is in these signals, and we can turn that to our advantage. So we just talked about a way of using them to inject electricity to interrupt brain function, but instead let's look at what we can measure in them. This is just another cartoon to illustrate what an ECoG electrode is, sitting on top of the surface of the brain, the cortex, and zooming into one example electrode. This is the tissue that it sits on top of. And we estimate that ECoG is measuring typically the activity of about 500,000 cortical cells at a time. Now, as the technology improves, our resolution is improving, which means we measure with smaller electrodes and smaller populations of cells, but the principles at this level scale parametrically. So we can make specific statements about the activity of the population of cells underneath each of these recording electrodes. And if we want to talk a little bit about the spectral properties again, the signal processing, I said in the beginning with EEG, the scalp and the skull acts as a low-pass filter. It passes only low-frequency activity, and everything else it filters out, which means you've significantly truncated the usable information range available in EEG. With ECoG, you can look at the entire broad spectrum band of activity that you can detect above a population of cells. And it's this high frequency band, about 80 to 110 hertz. This is in contrast to the alpha signals we were seeing before at about 10 hertz. This signal closely tracks the specific function of the patch of neurons underneath that recording electrode. So increases in that power band indicate a cortex that's very active. It's doing whatever that job of that part of the brain is supposed to be doing. Decreases in that high-frequency band show inactivity. And so we can use that to our advantage. How many of you have seen the homunculus? Should be familiar. At least one. All right, most of you. This is the motor or sensory homunculus, and this is again stemming from the same studies in the 50s. I think it was first published in 1952 by Walter Penfield. And there's a stereotype representation of the body that maps to different parts of the cortex. This is a lateral area here, and as you progress posteriorly, you emphasize disproportionately those areas of your body that are innervated most densely. So face areas you might find here, and areas you might find here. And if we ask a subject who has ECoG electrodes implanted to do something like stick out their tongue versus move their hand, we can measure ECoG signals and localize exactly where they're coming from in their brain. which means we can differentiate hand movement from tongue movement just from reading the signals and without having to inject any current. In fact, the signals are so good that you can actually dissociate different fingers. What we're looking at here, in the blue, the green, and the magenta, are 3 different recording electrodes over one patient who's been implanted with this entire ECoG grid. And you're looking at signals magenta from a data glove that records the position of the fingers. And you're looking at, in the colors, blue, the position of the thumb, the index finger, and green, and the little finger down here. And what you see is this match between the individual fingers and the changes in the brain signals at that location.
So it's the tongue is the language.
I'm sorry?
It's the tongue, region is the language.
Actually, in this case, tongue means specifically just the ability to move your tongue. So it's related, of course, to language, because without laryngeal control in the tongue, you can't really talk. But we would typically be talking about that as a motor mapping function in contrast to language function, which we would see in those receptive and productive language areas we saw before. That would be, for example, there it was. Yeah. So that whole mapping procedure in motor mapping, you might find tongue down here and hand motor up here, but language we would find here and here. Of course, the conjunction of the 3 are all necessary for language.
And now you'll see the 3.
Okay, so not only do we have that incredible spatial resolution, but we also have signal fidelity that's just unparalleled with ECoG. So this is a study I did during my doctoral work, kind of pushing the limits of what we could do with these signals. We talked about how in EEG we like to cross-trial average as a way of revealing signal that's usually masked by noise. This is a way of tracking the different functions of the brain, performing a stimulus-response task in a single trial. So here you're looking at ECoG activity recorded from each of these electrodes from the onset of a stimulus that the patient's been instructed to respond to as quickly as possible with a button press. And you can see very clearly how the signal forms a trajectory across the brain that's completely related to the transformation of a sensory stimulus to a pre-planned motor response. And this is a single trial, no averaging, no fancy signal processing at all. So the spatial resolution, the signal fidelity, and the temporal resolution are just unparalleled. Now, all of that was kind of post-processed data. To be clinically useful, we'd want a system that makes use of this information in real time. And this is technology, again, developed at the Albany Medical Center and the National Center for Adaptive Neurotechnologies in Albany, New York, by a very talented pair of scientists, engineers, Peter Brunner and Gerwin Schall, who's my PhD advisor, and talented neurologist Tony Rotaccio. He's now at the Mayo Clinic in Jacksonville. They were the first to develop this algorithm to take advantage of ECoG signals and map function. And this is a prototype user interface from a little over 10 years ago. Looking at the patient here, the results on a 3D cortical reconstruction here, and the ECoG signals here. These are just 2D representations of the ECoG grids. And in contrast to that stimulation mapping we saw, which takes, again, 3 to 8 hours, sometimes over 2 days, we can ask a patient to perform a behavior like hand motor, and within seconds, we localize that activity precisely on the cortical surface. At the time, this solution was absolutely over-engineered. It doesn't even need to take as long as it took then, which all said and done was about 12.5 minutes to dissociate these 4 different areas of sensory motor function. So So you're seeing in real time the map that we developed in the clinic from measuring ECoG signals and doing some signal processing on them. This is compared to a map here that the neurologist developed after 2 days of mapping, 3.5 hours, split up actually by the first term being interrupted by a seizure elicited by the stimulation. So 2 days, 3.5 hours to get what this does now in 10 minutes. And like I said, that was 10 years old, so now these systems are commercially available, they're inexpensive. And this is from work done by a colleague in Japan. I think it's Asakawa Medical University. His name is Dr. Kamada. He's a really, really brilliant surgeon who's pushing the envelope with a lot of current technologies in his clinical applications in surgery and epileptology. The other nice thing about this technique is that it has proven quantitative and qualitative concordance with the stimulation mapping. So in the blue, you can see what the stimulation electrical current projection comes up with, and in the red, what the ECoG maps come up with in seconds or minutes. And what you can immediately see is that they hit all of the same spots, and in fact, they tend to be even a little more sensitive. And the difference there is because ECoG is not a lesional approach, it's not only detecting those areas that are necessary for function, but also those that might contribute in subtle or nuanced ways, meaning that if you interrupt them with current, it won't give you an overt change in behavior that can be seen in a clinical setting. The effect might be so subtle that it would take months for someone who knows the subject well to determine. So not only is it faster and equivalently effective, it also might be more sensitive. This is an ongoing area of research that's gotten a lot of attention recently. This is something that we've just been working with recently, high density grids, 256 channels, and it allows us to start to dissociate even different parts of your receptive language areas in ways that we haven't been able to do before. And there's some evidence that this can be done in an anesthetized brain as well. Now, we're almost at 5 o'clock, which is actually good timing. I wanted to leave you with something that I always love. This is some more stuff from the brain-computer interface world, headed by a colleague of mine. He's just a brilliant academic engineer, Christoph Kappeler, working again with Dr. Kamada in Japan. This is a real-time brain-computer interface system that's designed to look at his brain signals and determine in real time whether he's looking at a face, a symbol, kanji, or neither. So you can see that it works fairly well with pictures. The experimenter is going to show him his face, so we know it's not just photographs. It works in a mirror, and it works with an unfamiliar experimenter. That's Dr. Capella there. And at this time, this kind of signal processing is trivial, and patients with these procedures are relatively common. So we're just beginning to scratch the surface with what we can do with electrocorticography as a tool. And these are just some of the highlights and some of the interesting areas that are continuing to evolve and that I've been very, very fortunate to be able to participate in, mostly under the leadership of project leaders who are just phenomenal academics. So I hope that gives you kind of a very quick, I know I kind of rammed right through it there, apologies for having to start late, but a little bit of an overview of what these signals do, what we're doing with them, and where we're going with them next. And if you have any questions or follow-ups, please feel free to drop me a line. That's the best email to reach me. I promise I'll give you a response as quickly as I can. And I think I will probably make some or most of these slides available to share as quickly as possible. Some of it I can't share because it's not mine to share other than with you today. And with that, thank you again for your attention and for the opportunity to bore you for 45 minutes.
excellent lecture. I think it's a really amazing, overview. And
Thank you.
Just a short time, some EEG, some stuff, analysis, everything. Good.
Yes.
As we know, you use this kind of machine, we can detect the human brain signals and recognize this kind of pattern. But I'm very curious. Have you guys reversed those signals to the human brain and human-computer interact to try to reverse those kind of things?
Yeah, if I understand your question, and it's a good one, there's a lot of stuff working on translating sensors or tactile devices into sensation. Yeah. So the old paradigm, as you were saying, the old paradigm is to take brain signals and translate that into output, like the BrainGate people at Brown University are using these signals to control robotic arms. But like you're saying, the real hot areas, the real next stuff, if you want to be really cutting edge, is the other way. How can you develop a sensor that translates for someone who's lost a limb into feeling in that prosthetic arm? Not just the ability to move it, but the ability to have fine sensation in those digits. If you, if you can get that working, you'll be a very rich man very fast.
Yeah. Maybe some days we did not need our body, just the brain, and we can create the immortal.
It used to be science fiction, but the more we're close to it being fact.
Yes, and there won't be any further education because just connect to the computer and anything just.
We just download lectures.
Yeah.
One day.
Any other questions? Okay, we're starting. I know it's getting late. I'm sorry about the little taggy probably in the beginning. But really, it was a wonderful, wonderful lecture. I really
It was a
appreciate
pleasure
it.
to be here. Thank
On
you.
behalf of the class, thank you so much. Have a nice weekend.
You too.
Okay. Okay, good. We're probably going to have a little bit of time. Give us a wrap up the first week of our training class, and I want to hear from all of you. Give us some feedback. We have another week to go, and anything that you like, or anything you saw. No comment. No comments. No suggestions. Not good, not bad. Just want to be very constructive. I know you guys
Just send it to me and I'll give it to them.
Okay.
And we really appreciate you speaking. Sorry.
I'm glad it worked out. It was fun.
You may already see the schedule, just to see, something you want to hear more, something you want to adjustment. I can do that in my lecture. You know what I mean? Actually, I leave some spots for myself.